Welcome to the Math Record. Today we'll be learning about the chi-square goodness of fit, which is also known as the chi-square GOF, usually. This video will cover Chapter 4, Part 1 of our statistics class. So, a chi-square goodness of fit. Chi-squared goodness of fit, which is just GOF. Which is, basically, chi-square tests are all skewed. So it's basically like this. And then we use this skew graph to measure distribution to see if it's really unusual, basically. So for a chi-square goodness fit versus a chi-square test of homogeneity and a chi-square test of independence, a chi-square goodness of fit uses a frequency table, while a homogeneity and independence use a contingency table. So, sorry I spelled that wrong, but you get the idea. But the general idea is that if you see like a chart, right, and it's like basically one variable and like something like, let's say like the amount of reds and the color and the amount, right? So you have a red, blue, and green, right? And you have like 2 red, 3 blues, and like 5 greens. Then this is a frequency table. That's when you use goodness of fit. For contingency, right? It's basically like we have something like this. You know? Like you have like yes and you have like variable 1, this 1, 2, 3, 4. Variable 1, variable 2, variable 3, and variable 4, and then you have like four numbers in here, right? So it has like it's a 2 by 2, while this frequency table is just one number, right? So when you see a frequency table, you're gonna use a chi-square goodness of fit, basically. So as always, when you're starting with the test, you're gonna have to do the conditions. Okay. For a chi-square goodness of fit, it has to have count data, which basically means the data must be able to count it. The data is counted. Like in our example where we use red, blue, and green, we could count the amount of reds, which is 2, the amount of blues, which is 3, and the amount of greens, which is 5, right? So the data should be able to be counted. And then you have independence. All the tests have this, which is basically no, the data is independent of each other. So data is independent. So just because you got a red like the first time doesn't mean like it will affect the probability of getting the red the second time, basically. So that's independence. Random. The sample is basically random because you don't want it to be like data skewed. The data is sample is random. Is random. This is usually done by using like a SRS, a simple random sample. A random. You have a 10% condition, right? Which basically states that your sample size, which is your sample size, which is referred as n, is less than 10% of the population that you're looking for. So if you have like 10 marbles, that means that 10 marbles is your sample size, and there should be over 100 marbles that are like made by that like company or something. So you have to put it in context all the time. Expected frequency. This is what we're gonna use for chi-square tests. The extra thing that we had to do. Each like test has an extra thing, and for chi-squared, goodness of fit is the expected cell frequency, which basically sorry, I forgot the U frequency, which basically means that every cell is greater than or equal to 5. So the expected number. So for our red, blue, and green example, right, there was a 2, a 3, and a 5, right? So that is what your sample is. Your expected cell is like let's say we have we have a table, right? And we have red and blue. Let's just have that. And the amount of red is 10 and the amount of blue is 20, right? And you expect there should be equal amount of red and blue. So the expected table is red and blue. So equal amounts 20 plus the 10 is 30. So 30 divided by 2 is 15 because it's equal. So each of them have 15, right? So so our sample is 10 and 20, which is what we actually got, but our expected is 15 and 15 because they should be equal, right? So our cell states that this table, right, the expected table, each of the cell has to be greater than 5. So the 15 red is greater than 5, the 15 blue is greater than 5, which basically what the condition states. So after you're done with the condition, you could use the transition statement, which what you do for every single test. This is very simple. Yeah, it's the same for the first part for all the tests. Since the conditions are met, are met, I can construct a chi squared like goodness of fit, which you just write GOF basically. If you want to write goodness of fit out, you could goodness of fit, if you want to. But GOF is fine. There's only 3 types of chi-squared anyways. There's goodness of fit, there's homogeneity, and independence. In the next video, we'll be covering homogeneity. But in this video, we're going to be covering the goodness of fit. After homogeneity, we'll be talking about independence. Okay, the actual test. So our null hypothesis is a statement. So while our models and our Z models use the idea that like a mean or a proportion is equal to this true mean and true proportion, for chi-squared tests, you're gonna be talking about like the distribution. So it's not just one value; it's like a range of numbers. So you say the distribution, your your null hypothesis is that the distribution um uh, is the same. But you always have to put this in context. So you can't say like the distribution or what is the same. So you have to put this in context. I'll show this later on when we do an example in the end. And the alternative is the hypothesis if is the distribution is not the same. So null is the same and alternate is not the same. Isn't the same, basically. Okay. Now, now we don't really have to define our variables on this because usually you're not really using these kind of variables. What you're gonna be doing is that you're gonna put these into charts and you just gotta look at the chart and you gotta be comparing charts. So you don't have to like do the define variable sets as like the T model and the Z model. So now the mechanics. All right. You always have your alpha level, right? Let's just write that out first. Let's say it's 0.05. It's usually 0.05. If they don't specify, it's 0.05. Let's say ask you to like change it to like 0.01 because that's what the question is asking for like a 10% that you think might be wrong. Okay. And now you have the x squared, which is equal to the summation of basically the observed minus OBS, which I'm just going to call observed, minus the expected, which is EXP, and then square that number, and then divide that basically by the expected. And this has a degree of freedom of the n minus 1. So how much numbers you have minus 1, basically. So when our example of red, blue, and green, that's 3, so n is equal to 3, so 3 minus 1 is 2. So we have a degree of freedom of 2, for example. Right? And then we use this to get a value for x squared. So then we have a p-value. Our p-value is going to be equal to Because while like the T model and the Z model uses a Z score and a T score, our mechanics we really didn't have to do that. So basically, we're just gonna plug this into like our calculator, and we're gonna use the x value in our calculator to get this this basically area. So our P is that it's the x value with the degree of freedom of whatever your degree of freedom is, basically, right? And it's greater than equal to whatever you get for this number. So x squared, the actual number. Because you actually write this out. I'll show you what you're gonna write later in the example, anyways. And that's basic for the mechanics. And then for the conclusion, it's generally the same ideas like the Z test and the T test for conclusion. So if your p-value, right, is less than 0.05, you say the null hypothesis is true. You say your alternative hypothesis is if your HO is true, you're gonna if your p-value is less than 0, your null hypothesis is false, and you say your alternative hypothesis is true. And if your p-value is greater than 0.05, your null hypothesis is true, and you say your alternative hypothesis is false, basically. But you have to write this in context, and you basically write it in these words. So you say, based on my p-value of whatever your p-value is, which is either greater than or less than the level of 0.05. So if it's like the p-value is less than 0.05, we say, based on the p-value of whatever your p-value is, which is less than the alpha level of 0.05, because that's the alpha level, I fail, I reject the null hypothesis. There's evidence to suggest the alternative hypothesis is true. You have to write this in context. So talk about what your null hypothesis is. Talk about what your alternative is. And then if your p-value is greater than 0.05, your alpha level, you say based on my p-value of whatever your p-value is, which is greater than the alpha level of 0.05, I fail to reject the null hypothesis. So talk about your null hypothesis in context. There lack evidence to suggest the alternative hypothesis is true. So talk about your alternative hypothesis. Okay. So usually for like T models and Z models, they always follow it up with a confidence interval. This works because like a Z model looks like a normal bell curve, right? And then you have a T model which is more flattened out, right? So these models, a Z and a T, they are both symmetric. So you could use a confidence interval to get like some kind of range, right? So you have some kind of range between these numbers. For a chi squared, right? Chi squares are basically skewed, so they look like this. So you can't really do a right confidence interval, because it doesn't work, you know, because it's not symmetric. So since it's skewed, you can't use a confidence interval. So you usually just use a test only for a chi squared. So for chi-square goodness of fit, chi-square test of homogeneity, and a chi-square test of independence. All these basically just use a stat test and no confidence interval. So let's actually work on an example. Let's say some kind of chocolate company, right, states that 40% of their chocolate is red, 25% is blue, 20% is green, let's say, and oops, sorry about that, green, and 15% is yellow. So all those percent should add up to 1. So 40 plus 25 plus 20 plus 15 should be 40, which is, so that 25 plus 15 is 40, plus that 40 is 80, plus the 20 is 100. So that should be equal to 100%. So that makes sense. And let's say your sample, right? Based on your sample, you are given you have 33 red, you have 33 blue, You have 25 green, and you have 9 yellow, right? So based on this amount, we basically just look at so this is just 33 plus 33 plus 25 plus 9, which is 100. This is a sample size of 100. So we have 100 as a sample size, right? So based on this, let's kind of I'll hide this for a second, and we'll actually do the So the first thing is that we want to do the conditions, right? So it must be count data. So the data is counted. So the amount of the co- um the the amount of chocolate could be covered. It's basically amount of chocolate per color is counted. Per color is counted. You have to always put this in context. So in this case, we'll be talking about chocolate, and we have independence. So color is independent of the amount is color. The amount is independent of color. Is independent of color, right? Because just because you got a red marble this time doesn't mean you're gonna get like a red marble again. You know, random. You took a random. The question gave us that the we took a random um chocolate sample, right? And a 10% condition, which is basically your sample size is less than which is equal to 100 because we have 100 from our sample. It's less than 10% of all the um marbles made by that chocolate made by that company, which is true, I guess, because you could just assume that they make more than 100 chocolate because they're a company. And let's get this out. And now we actually have to do the chart. So going back to our thing, we have we have to do the expected frequency table. So this is what be our expected frequency condition. So we have the chocolate color and basically the amount. So we have red, we have blue, we have green, and we have yellow. So remember our sample size is 100, right? So 40% of 100 is 40. So our red is 40. 25% of 100 is 25. 20% of our 100 is 20, so for green, and 15% of 100 is 15. So we have 40 red, 25 blue, 20 green, and 15 yellow as our expected. But for our sample, we have 33 red, 33 blue, 25 green, and 9 yellow. So that is our basically our sample frequency table, while this would be our expected frequency table. So our conditions, our expected frequency, expected cell frequency condition, states that each cell has to be greater than 5, which is true because 40, 25, 20, and 15 is greater than 5. Okay, so that's true. So let's delete this. Now we just need to work. Now we just write our transition statement. I'm not gonna write it. You just say it out verbally. You could just say. I'm just gonna say it out verbally, but you have to write this down basically if you're doing the test. Say since the conditions are met, I can construct a chi-squared goodness of fit. So whatever I wrote in the beginning of the video, basically just write that transition statement, and then you have your test. So your null hypothesis is the distribution um for the color of chocolate is the same as the company's claim. right? So they claimed that 40% was red, 25% is blue, 20% is green, and 15% yellow. So we're saying our sample has the same distribution, or somewhat the same. And then we have alternative hypothesis, which says the distribution for the color of chocolate isn't the same as the claim, basically. Isn't the same as the claim. To put these all in context, right? I didn't just say the distribution is the same and the distribution isn't the same. I said the distribution of the color of the chocolate. So you have to put everything in context and be like the company's claim, the color of the chocolate. Give everything in context when you're doing these questions. So that's the test. Now let's actually work on the mechanics. So your x squared is equal to basically whatever you have observed minus your expected, right? So let's draw our table out again. So we have, sorry about that. We have red, blue, green, and yellow. And we have 40 for red. We have 25 for blue. We have 20 for green and 15 for yellow, right? And that's our expected. So I'll write E down here for expected. For sample, I'll put S. Our sample, actually, let's move this a little upper. Expected in our sample. Okay. So let's write our down for this one. We have red, blue, green, and yellow. So for our red, for our sample, our red and blue was 33. And our green is 25. And our yellow was 9. Right? So this is based on our company's claim, and this is from our actual sample that we got. So our x squared is equal to our the summation, so the sum of each one, the red, blue, green, yellow, of the observed minus the expected, and then you basically square that number, and then you divide by the expected again, and then you basically have a degree of freedom of n minus 1. So let's do the math on this. So we have observed minus expected and square it. So we have 33. 33 minus 40 squared divided by 40 because that's expected, and then you add that number by 33 for the blue minus 25 for the blue, square it, divide by the 25. Then you add the 25 minus the 20 squared, and then divide that by 20. And then you add a 9 minus the 15, and then you square it, and you divide that by a 15. Right? And then you basically add them all together, and you get an x squared value of 7.435. And then we have a degrees of freedom of basically the amount of cells you have. So you have, which was n minus 1, right? Our actual n is actually the sample size was 100, but this n is different. This n is basically the number of cells. So you have the red, blue, green, and yellow, so that's 4. So that's 4 cells, right? Because there's 4 different colors. And then 4 minus 1 is 3. So you have a degree of freedom of basically 3. Right? So now you have to use the alpha level of 0.05. And then you have a p-value is equal to your p, which is x squared, with the degree of freedom of 3, because that's your 3, is greater than or equal to your p-value, which is 7.435. And you gotta use your calculator for this. So go to your calculator, go to calculate, which is A, menu, probability or statistics doesn't matter. Just go down to distribution. Then go down to X squared CDF, which is number 8. And then you want a value bigger than 7.435, right? So your lower bound would be 7.435. And your upper bound would be, you could just write 9, capital E, 999. And your Nspire, I'm using an Nspire. So on your left, right, if you just go all the way down, there's a EE, and above that is a pi symbol. Below it, that is a pi symbol. Just press the EE button, basically. So it's the 9, then press the E once, and then 9E, 999. E basically just stands for 10. So it would just be 9 times 10 to the power, like 999. It's just a really big number, basically. That's the general idea. So we just put a really big number. It doesn't matter. You could put like 1 million, 1 trillion, 1 billion. It doesn't matter. Or just put like a really big number. And your degree of freedom is basically 3. And press OK. And you get a p-value is equal to 0.0593. Which is a little bit bigger than our alpha level of 0.05. So this tells me that we failed to reject the null hypothesis. So we say our null hypothesis is right because it's not that unusual. Even though it's just a little bit above 0.05, it's still above 0.05. So that's the point. So now we basically write our conclusion. So we say since the p-value of 0.059, right, is less than the alpha level of 0.05, I fail to reject the null hypothesis. And then you say there lack evidence. There lack evidence to suggest the alternative hypothesis is true, right? So you have to write this in context. So don't write the HO, write actually in words the null hypothesis. So since the p-value of 0.059 is less than the alpha level of 0.05, I fail to reject the null hypothesis that the distribution of the color of chocolate is the same as the company's claim. I fail. Then you say there lack evidence suggests that the distribution. There lack evidence suggests the distribution of the color of chocolate by the company isn't the same as what the company claimed. So, which is the alternative hypothesis. So basically, write that. So this basically tells us that you failed to reject the null hypothesis, so you did not reject the whole null hypothesis. So you're saying the null hypothesis is right, and you say there's lack. Sorry, I forgot. I have to write right here. There lack evidence. Sorry about that. There lack evidence to suggest the alternative hypothesis is true. We didn't say that there isn't evidence that the hypothesis might be true, and we didn't say the alternative hypothesis is not true. We just said there isn't enough evidence to tell us that it might be true. So that's the general idea. So that's what happens if you do it by hand. If you do it by calculator, which I'm using an Nspire, just go down to your list and spreadsheets, which is like the fourth icon on the bottom that's green. Press enter. And then you have column A and column B. Let's just call column A our sample one, right? So type sample right next to the A, column A. And then right next to column B, we're going to call it our expected. So EXPECTED, or expected, right? And then you basically put your sample. So let's say row 1 is the red one, which is 33, Row 2 is the blue one, which is 33. So, and row 3 is the green one, which was 25, and row 4 was the yellow one, which is 9. And for expected red, it's 40, then it's 25, then it's 20, and then it's 15. So your spreadsheet should look something like 1, 2, 3, right? So you have something like sample, and then you have expected, and then this is the first, second, and third, fourth. So the first one is the red one, which is your sample is 33, then it's 40, then it's 33 and 25, then it's 25 and 20, and then it's 9 and 15. So this is the red, this is the blue, this is green, and this is the yellow, right? So put that in your chart, and then go to a different white square on your Nspire, press menu, press number 4, which is statistics, then go down to number 4, stats test, and then go down to number 7, which is X squared GOF, which is goodness of fit. And then your observed is basically your sample. So you say your is your sample, right? So, and then your expected is your expected. So just go to your expected, and then your degrees of freedom is 3 because you have red, blue, green, and yellow, which is 4. So 4 minus 1 is 3. And then you can just leave whatever your first result column is. It's usually some other column other than A and B, which is fine. And then press OK. And then you basically get your the entire test based on your calculator. So you get an x squared value of 7.435, which was what we got, a p value of point 0.593, right? 0.0593. So that was our p value. We get a degree of freedom of 3, and then we have a basically a list on the bottom, which you don't really have to focus on. So those are the only values that matter. So if you don't want to do the math, you could basically just put this in your spreadsheet, and you basically do everything. So that basically covers everything for the chi-square goodness of fit. Thanks for watching, and I'll see you at the next math record.